In this screencast, we will quickly review properties of exponential and logarithmic functions, as well as the idea of using inverses to solve equations. Then we will practice solving exponential and logarithmic equations. Previously, we looked at the exponential functions p of t equals 10 to the t and e of t equals e raised to the t, as well as their inverses, the natural log of y equals log base 10 of y, and n of y equals the natural log of y. We emphasized that because they are inverses, they say the same thing from two different perspectives. We know t is the power to which we raise either 10 or e, and y is the result of raising either 10 or e to a particular power t. We also saw that since the domain of the exponential functions is all real numbers, the range of the logarithmic functions is also all real numbers. And because the range of the exponential functions is all positive real numbers, the domain of the logarithmic functions is also all positive real numbers. While this may not seem significant up to this point, it will prove to be significant later when solving logarithmic equations. So again, the domain of a logarithmic function is all positive real numbers. Lastly, we saw that log base 10 of 10 to the t equals the natural log of e to the t, which equals t, and 10 raised to the log base 10 of y equals e raised to the natural log of y, which equals y. This is related to the fact that when we apply inverse functions to each other, their processes are reversed. Believe it or not, when we solve equations, we're actually using inverse functions to reverse a process. In your past studies, you probably learned about the order of operations. You were taught that when simplifying, we simplify parentheses, exponents, multiplication and division, and lastly, addition, subtraction. Well, when we solve equations, we are reversing the simplification. So when we solve an equation, we reverse. We do addition and subtraction, then multiplication and division, then exponents, and lastly, anything in parentheses. You may have noticed that in PEMDAS, the inverse of adding and subtracting are already paired together, as are multiplication and division. And although logarithms are not explicitly listed in the order of operations, we know that logarithms reverse exponential functions. So let's apply this logic and solve some exponential and logarithmic equations. All right, so we're going to solve each of the following equations exactly and then find an estimate that's accurate to 5 decimal places. In our first example, we have 10 to the t power equals 1 over 265. We know that we are solving, so we are going to work on undoing the order of operations. There's no addition or subtraction, there's no multiplication or division, so our first step is immediately to figure out how to undo this exponential function, and we know the inverse of an exponential function is a logarithm, so we could rewrite this as a logarithmic function. Log base 10 of 1 over 265 is going to equal the power to which we raised 10 to get 1 over 265. So this is our exact answer for t, log base 10 of 1 over 265. And if you use Desmos or a calculator, you will see that t is approximately negative 2.42325. You should definitely pause the video and make sure you can actually get that decimal approximation on your technology. All right, the next example is log base 10 of y plus 5 equals 2. We do see some addition, but that is inside the parentheses, so that will be one of the last things we worry about as we solve this equation. We don't see any multiplication or division, so we will deal right away with trying to undo this logarithmic function, and we know that exponential functions reverse logarithmic functions. So we know that 2 is the power to which we raise 10 to get y plus 5. So 100 equals y plus 5, and y equals 95. Now, if you remember on one of the previous slides, we mentioned that the domain, so the input here, must be all real positive numbers for logarithmic functions. So we should always double check that the solution we found is in fact positive when we add it to anything else that was inside the function. So 100 is greater than 0. This checks. That means the input to the logarithmic function would be a positive real number. So y equals 95 is a solution. All right, let's move on to 2 more examples. The directions are the same. We'll give exact answers and then round to 5 decimal places. Why don't you pause the video and try these ones on your own? Okay, so remember when we solve an equation, we are going to work to undo the order of operations. So we see in this first problem, 3 minus 5 natural log of y equals negative 11, that we do have this 3 that's actually being added. So we're going to subtract 3 from both sides. Negative 5 times the natural log of y equals negative 14. And then we see that the natural log of y is being multiplied by negative 5. So we'll divide both sides by negative 5 and get 14 over 5. So at this point, we've undone addition and subtraction. We've undone the multiplication or division. And now we are looking at undoing an exponential function. Well, a logarithm is a different way to think of an exponential function. So in fact, we will reverse this logarithmic function by rewriting it in exponential form. We know that 14 fifths is the power to which we raise e to get y. So this is our exact answer for y. And again, using whatever computational device you prefer, we would get y as approximately 16.44465. And also remember that the input, right, the domain of the logarithmic function needs to be a positive real number, and 16.44465 is a positive real number, so that checks. We can in fact say that our exact answer is e to the 14 over 5, or approximately 16.44465. All right, here's our last example. Negative 3 plus 1/2 e raised to the 2t equals 9. Again, we're solving, so we'll undo addition or subtraction first. So we see this negative 3. We're going to reverse that process by adding 3 to both sides. We have 1/2 e to the 2t equals 12. Then we will reverse this multiplication of a half by multiplying both sides by 2. So we'll have e to the 2t equals 24. We're at the point where we have an exponential function, and we will reverse that by using a logarithmic function. So we know that we could write this as the natural log of 24 equals 2t, and then to isolate t, we'll divide both sides by 2. So this is our exact answer, and using a computational device, we find that t is approximately 1.58903. So I hope this video has helped you in your thinking about how to solve exponential and logarithmic equations.